Well, thank you for tuning in and also giving me the opportunity to present some of my recent research. So I recently moved to Cambridge, and I will be talking about formation variability of star formation and how this is also linked to the formation of bulges in galaxies. So here I'm talking about bulges in a more classical sense, talking about spheroidal components in galaxies, both the ones that we see on small scales in star-forming galaxies, but also on large scales that can dominate the whole stellar structure in quiescent galaxies. And so why do we care about bulges and the stellar structure in general? Well, this is because they encode the formation and evolutionary processes of galaxies. And so there is this very nice link between the star formation and morphology. In particular, when we look at the star formation distribution in the galaxy population at redshift 0, so today, we can see that there are these star-forming galaxies and these quiescent galaxies. And when we look at their stellar structure, we can see that the star-forming galaxies are typically these disk galaxies with nice spiral arms. And many of those have also a bar or a classical bulge component in their core. And then when we go to more massive galaxies, we can see that their stellar structure is typically a bit more boring, right? They seem to be much more homogeneous. But there is also an interesting density. If you look at the kinematics of the stars, we can see that the lower mass quiescent galaxies are typically rotating quite fast. So these are sometimes called fast rotators. And then when we go to more massive galaxies, we can see that they are rotating more slowly, and their stellar structure or the kinematics is dominated by random motions. And so this, of course, indicates already different formation channels, right? That fast rotators probably form, through rather dissipative formation processes, whereas when we go to the slow rotators, we are looking at objects that are formed through mostly dry mergers. So if you want to understand how, in particular, quiescent galaxies form, we can see that at redshift 0, that these galaxies are not directly linked to each other, right? These star-forming galaxies are not the progenitors of these quiescent galaxies. They just have too little star formation to grow and produce such massive systems anymore in today's universe. And so if we want to understand, how those massive galaxies form, we have to actually go to earlier cosmic times. And thanks to the Hubble Space Telescope, but also to very large telescope in Chile, for example, we were able to map out the redshift 2 galaxy population in much greater detail. And so we have been pushing some of the current facilities really to their limits to trace the detailed structure of these galaxies around redshift of 2. So this is roughly 3 billion years after a Big Bang. And so we have been using we have conducted the largest adaptive optics spatial results spectroscopic survey with Symphony at the VLT. And we have also at the same time obtained the Hubble Space Telescope images, such as those you can see here in the background. And so here, this has been really a major work in the past years. And so here I'll show you one of these galaxies around redshift of 2. And again, the Hubble imaging gives you basically the stellar population distribution in these galaxies, whereas with Symphony, we are able to trace the H alpha emission line, which can give you the kinematics, but also the star formation distribution, because H alpha is an exquisite, tracer of the star formation. And so we have been mapping out the stellar mass densities and as well as the star formation distribution in these galaxies. So here just I'm focusing on the most massive sample. And you can see that the stellar mass density is actually quite concentrated. We have in the center, in the core region, stellar mass densities that are very comparable to local early type galaxies. And then the star formation is distributed in a much more exponential disk. And so when we look at the specific star formation distribution, we can see that the specific star formation is actually suppressed in those massive galaxies in the core. And so they are not really forming anymore their stars there. The growth rate of new stars formed there is much lower than the stellar mass that is already present. And so what you're observing is that these galaxies are probably quenching from the inside out. And so the centers have already made a very strong bulge component. Okay, so they show these galaxies that are at redshift 2 show mature bulges in their core. And another way to look into this is what I show you here is from the very same paper, the stellar mass density within a kiloparsec as a function of mass. The circles are the redshift 2 galaxies. And you can see that those galaxies line up with quiescent galaxies at redshift 0 very well. Okay, so this means that the stellar mass density is already present in these massive galaxies. You can also do bulge disk decomposition, and Philippe Lang has done a very nice analysis using the stellar mass maps. And you can see here that for these galaxies, even for star-forming galaxies, the bulge to total ratio at the massive end is of the order of 50%, right? So about half of the mass in those galaxies is in a bulge-like component. And so the question then, of course, is on a theoretical side, how do you form such bulges at even earlier times, right? They are already present at redshift 1 to 2. So how do you form them before that? And for this, I've been looking at the VLOG cosmological zoom-in simulations. And I show you here just a cartoon picture with some of the science figures of the paper. But what we have found is that galaxies self-regulate when they grow on the star-forming main sequence. So the galaxies are moving up and down the star-forming main sequence on a wide range of different timescales. And I will be talking at the very end of my talk about this a bit more. But we can also see that the distribution of star formation actually depends where the galaxies are relative to the star-forming main sequence. And so this is because when we look at the gas distribution, so these galaxies are actually at these early times quite gas rich. They are much more turbulent, but they're still typically having some rotation in the gas disk. But it's much less stable. So even a counter-rotating stream is able to lower the angular momentum of the gas disk, so that a lot of gas, falls into the central core. And this leads then to a nuclear starburst, okay? And of course, also mergers can trigger this. So this is what we call then the compaction. You can see this here. The gas surface density now in this phase is significantly elevated in the central region, which then leads to a specific star formation. The profile is not anymore flat, but increasing towards the core. And so this then leads, of course, to a lot of star formation. And the star formation itself, well, the gas gets consumed into forming stars, but the stars also produce outflows, which then tries to quench the galaxy. And so that's why there is this self-regulation that then the galaxy basically tries to quench. But typically the replenishment time of the gas disk is short. And so you are able to reaccrete gas, in particular in the outskirts on quite short timescales, which then leads to star formation mostly in the outskirts. And so you have, when you look at the gas distribution, sometimes like a gas ring, and the specific star formation rate is rising as a function of radius. And you can go through such phases actually several times before you fully quench and are a quiescent galaxy. Now, can we observationally test this? And one way to do this is actually looking at the gas fraction or the depletion time as a function of distance in the star-forming main sequence. And so what I've shown here, these points are the simulations, and then the solid line and the green line is fit to this, and the red dashed line is from observations from Gensel et al. And you can see that indeed we overall reproduce these trends. So it seems that there is this self-regulation along the main sequence. Now the question is this related to the formation of bulges? And here again, I think looking at the specific star formation rate as a function of radius within galaxy, I think is crucial as a function of distance from the main sequence, right? And this is a very challenging measurement. So these are the simulations, right? So you can see clearly that galaxies, above the main sequence should have proportionally a higher specific star formation rate in the core relative to the outskirts. And this is then the opposite when you go to below the star forming main sequence. But this is a very challenging measurement because of the dust attenuation, right? So both the amount of dust, but even the attenuation law can change as a function of radius. And these are, I think, is a challenging measurement. So we have done some work on this using H alpha and UV as a star formation rate tracer. And we only have a sample of 10 galaxies where we have both. And we are currently following up with ALMA. There have been, of course, a lot of ALMA measurements on this. And typically they have been biased slightly higher, slightly focusing more above the star forming main sequence. And at least those measurements have shown that typically the ALMA sizes at 870 micron, which traces more the dust obscured star formation or the dust in general, have more compact sizes than what we see when we look at the stellar mass or the HSDH band. And so this indicates that indeed there seems to be a lot of nuclear star formation going on. But I think the jury is still out to measure this properly. And I think ALMA, but also in particular James Webb Space Telescope will help a lot with this. So now I talked about the VLA simulations. What are with other simulations? Well, If you look at illustrious TNG, which is of course a very different beast of simulation, I think we have much larger statistics there. So I've been looking at TNG 100 and try to understand where do spheroids build up, right? And here we are looking at all the galaxies. And the question is, well, okay, what's the fraction of mass growth in the bulge or in the total spheroid, where the bulge is just a spheroid component within the central 3 kiloparsecs. And so you look at 10 to the 11 solar mass galaxies, for example, you're asking, where do these galaxies form their spheroid component? And you can see that, you know, when we look at the bulge component first, so this is the spheroid component within the central 3 kiloparsec, you can see that about 70%, right, of the mass of a 10 to 11 solar mass galaxy has been formed while the galaxy was star forming. And only a small fraction when the galaxy transitioned to the quiescent phase or when it has been quiescent. These fractions slightly decrease, right? We expect that mergers are more important for more massive galaxies. And so we think that maybe in the quiescent phase, there is a larger fraction of mass growth in the spheroidal component. And you can see a very similar story asking the question, well, where is the specific bulge growth efficiency most, you know, where is specific bulge growth formation efficiency high, right, relative, you know, to the mass? And you can see that this happens mostly at lower mass, or, you know, for more massive galaxies when they were star forming at early times, right? So I think, you know, all of this shows that indeed you're building spheroids and bulge-like components, in particular for massive galaxies, while you're on the star forming main sequence at early cosmic times. So in the last 3 minutes, I would like to talk a bit more about these oscillations about the main sequence. They are not only important for understanding the formation of bulges, as I just highlighted, but also for understanding general, you know, processes that shape the star formation. And if you think about galaxies, right, they're not living in isolation. It's a complex system of large-scale structure and internal processes, going from, you know, interesting physical processes related to cosmological gas accretion to mergers, and then we have black hole feedback, reaccretion of outflows, bar and spiral arm physics, and stellar feedback and cloud physics. And all of these processes act on different spatial scales, right? But they also act on different time scales, going from giga-year time scales to, you know, a few million years. And so the question is, how can we learn more about these processes? Of course, one way to do it is to focus on nearby galaxies where we can spatially resolve most of these galaxies. But when you think about galaxies at redshift 6, okay, how can we make progress there? And the idea is to try to understand the star formation histories of these galaxies in more detail. And we put forward the idea that we can look at the power spectrum density of the star formation history to decode the physical processes that act on different timescales, right? So these different processes, they act on different timescales, and they ought to imprint themselves onto the star formation history that we then try to decode. Okay, so I don't think I have time to go into the details. What exactly we mean with the power spectrum density basically measures the amount of power you have on different fluctuation modes in the star formation history. And we have put forward this simple toy model where we basically extend the gas regulator model into a regulator model that is related to gas accretion, but then there's also internal processes related to the formation of giant molecular clouds. And we discuss different mechanisms that drive the stochasticity in the star formation history. The key thing is that, even we have the same processes with different timescales, they lead to very different star formation histories and different processes of how galaxies evolve relative to the star forming main sequence. For example, dwarf-like galaxies are much more stochastic. The GMC part of the model is much more important, whereas when you look at Milky Way-like galaxies, processes are much more smoother. Looking at high redshifts, the oscillations seem to vary as well. And based on this, we are able to say something about, for example, how the scatter in the main sequence should depend on the different star formation ray tracers. Okay. And anyway, there is much more to do today, more to do. So please stay tuned. And I'm, of course, very happy to discuss this more. So summary, I showed you that, there are clear indications from different observational probes that there are mature galaxies out to at least redshift 3, so about 3 billion years after the Big Bang. So this means that we have clear indication for quiescent bulges in the core of massive star-forming galaxies. And we believe that, we are witnessing the formation of typical M-star Early type galaxies. And of course, also, some of them will probably turn into slow rotators by redshift 0, depending on the exact merger history. These bulges are actually predicted in cosmological zoom-in simulations. So what we find is that these high redshift gas-rich galaxies, they can suffer from strong gas inflow into the core, what we call compaction, which can be triggered by mergers or counter-rotating streams of gas accretion. And so they evolve along the star formation sequence. So the regulation of star formation is directly linked also to the formation of these bulges. And so such models make strong predictions about the specific star formation rate gradients as a function of radius across the main sequence. And this is something that we can soon test with JWST, I think, much more accurately. Then we also discussed the star formation fluctuations, right? They are not only interesting for the formation of bulges, but they are actually much more interesting in a very general concept of understanding the internal workings of galaxies. And so here we have different processes that are encoded in star formation histories on different timescales. And the power spectrum density analysis of the star formation history will help us with temporally resolved galaxies that then we might not be able to spatially resolve. Okay, thank you very much. And yeah, I'm looking forward to the discussion.